In this screencast, we'll consider the problem, the puzzle of the Triomino tiling. It's a pretty old puzzle and fun to work with and to solve. Also illustrates how the problems can be solved via induction or recursion in computer science terms. So let's say that we have a board 2 to the n by 2 to the n, so this is 2 by 2 boards and of squares, small squares, and one of the tiles in that board is missing. So let's denote that missing tile by the blue color tile, and we have to cover such a board with triominos, which is a special a tile of a special shape, so that looks like this. So this is a triomino, right? So let me use the red color and okay, okay, let me draw another triomino, just rotated, and okay, so this is a triomino, this is another triomino, so we need to cover, for example, this board with triominos. So we do it like this, and this board can also be covered, and this can be covered, and this can be covered by placing a triomino like this. So like, for example, here's another bigger board, 2 to the n by 2 to the n. This is 4 by 4, so we can cover it like this. So place the first one, the second one, the third triomino, then the fourth triomino, and then finally the fifth triomino. So we got it covered. So let's say consider another example. Place the missing tile is here. So we place the first triomino, the second triomino, the third triomino, the fourth triomino, and the fifth triomino. So, or we can do it if we're implementing it in a program. We can use numbers. So this is the first triomino placed on the board. 0 is the missing tile. Then the third triomino is placed like this, and then the fourth triomino is placed like this, and then the fifth triomino is placed like this. And now we can do the tiling theorem, prove the tiling theorem by induction, which will show us how to solve the triomino tiling puzzle. So given 2 to the n by 2 to the n board, where n is greater than or equal to n, and a missing square, it is possible to cover any such board with triominos. So let n be greater than or equal to 0, then given a 2 to the n by 2 to the n board of squares, it can be covered with triominos, or can be tiled with triominos. And the proof will go by induction, and the source code that solves the link to the source code that solves that problem programmatically essentially mimics this proof via a recursion, which is a programmatic equivalence of induction. So if let's start with the base case. The smallest board is 2 to the 0 by 2 to the 0. So by definition, that smallest board has nothing but a missing tile, and they can be trivially tiled with 0 triominos. Now the next value of n is 1, and we have 2 by 2 board, and as we have seen already, any 2 by 2 board with a missing tile can be tiled with a triomino. Now if we generalize our solution, so let's say that if we have, for example, 4 by 4 or 2 to the 2 by 2 to the 2, right? So let's this is a 4 by 4 board, and we can partition it into 4 subboards, right? Or 4 quads. Say, for example, this is a missing tile, so we can place one tile in the center like this, and then tile each of the subboards or each quads recursively. So this is subboard tile, this subboard is tile. I'm going to tile this subboard and this subboard. So we can tile 4 by 4 subboards recursively with a missing tile. So, and in general, if we have, so let me say, right, this, this is another example of 4x4 subboard. So let's say this tile is missing in this subboard, so we can place our center tile and then tile each of the subboards recursively. So the trick, I'm just trying to develop an intuition for solving this problem. The trick is obviously to place the center tile in such a way that none of its squares is placed in the quad with the original missing tile. So if you let's say have and that's if you have a tile missing here, then and this is the subboards. If our original board is 2 to the n by 2 to the n, the 4 subboards, so the 4 quads, will have the dimensions 2 to the n minus 1 by 2 to the n minus 1. Right, and we know the row and column of the missing tile, so we place the missing tile, the center tile, start tiling by placing the tile in the center in such a way that none of its squares is in the quad with the missing tile. So in this case, it's like this, right? And then what we're going to do is we're going to do recursively tile each of the 4 quads by treating the squares of the first tile as the missing tiles in their corresponding boards, right? And of course, the square with the original missing tile doesn't have to be, already has a missing tile, okay? So this is inductive hypothesis. So assume, right? We're going to prove by prove by induction. On the base case has been shown. It's when n is 0, right? 2 to the 0 by 2 to the 0 board can be tiled. And then for the inductive hypothesis, we're going to assume that we can do it on the board, on the boards of size 2 to the n minus 1 by 2 to the n minus 1. Right? Assume that this can be done for n minus 1. And then consider the board of 2 to the n by 2 to the n. Right? So since we know the location of the missing tile, we can place the center tile in such a way that none of its squares is in the quad or 2 to the n by 2 to the n subboard with the original missing tile, and then recursively iterate and to tile the subboards, which can be tiled by the inductive hypothesis by treating the 3 squares of the original center tile triomino as missing tiles in their corresponding subboards. So here's another example. So the tile will be placed, let me grab the replica, like this, and then its squares will be considered missing in their subboards that can be recursively tiled again with triominos. So we tile this one, and this one, and this one, and this already has a missing tile.